Welcome back. Today we're going to answer the question that everyone asks. Why do diamonds sparkle? And more importantly, why do some stones sparkle more than others? Here's the secret. A gemstone in the dark is just a rock. Literally. Its entire beauty, its value, everything that makes it special. It all comes down to how it plays with light. That's it. No magic, no mystery, just really cool physics that we're going to decode together. We're going to follow a single ray of light, a photon, on its journey through a gemstone. Think of it like tracking a character through a video game. Our photon enters the stone, bounces around inside, maybe gets split into colors, and then shoots back out to your eye. Each thing that happens along the way creates a different aspect of beauty. The shine, the brilliance, the color, the rainbow flashes. By the end of this lecture, you'll understand exactly why a diamond looks the way it does, and why it's different from other stones. And I promise, no PhD required. Let's decode that sparkle. All right, let's map out our photon's adventure through a gemstone. Think of this as a road trip with 5 major stops. Stop 1. The surface bounce. Some light reflects right off the surface before even entering the stone. This creates luster, that initial shine you see. It's like when you see yourself reflected in a window. Stop 2. Getting inside. Light that doesn't bounce off actually enters the stone. How much light gets through? That's transparency. Think of it like the difference between looking through a clean window versus a frosted one. Stop 3. The bend. Here's where it gets interesting. When light enters the stone, it slows down and bends, like when you stick a straw in water and it looks bent. This is refraction, and we measure it with something called the refractive index. This bending is crucial because it determines if light gets trapped inside or just passes through. Stop 4. Getting colored. As light travels through the stone, some colors get absorbed while others pass through. The colors that make it through? That's what gives the stone its color. Think of it like a coffee filter. Some stuff gets caught, some passes through. Stop 5. The rainbow split. Finally, different colors of light bend by slightly different amounts. This can split white light into rainbow colors, creating what we call fire. Those colorful flashes you see when you move a diamond. 5 stops, 1 journey. Each stop creates a different aspect of beauty. Now let's dive into each one and see how it really works. First impressions matter, and in the gemstone world, luster is that first impression. It's the quality of shine you see when light bounces off the surface. Now here's a cool fact. How much light reflects off the surface depends on something called the refractive index, which we'll talk about more in a minute. But basically, materials with higher refractive indices reflect more light from their surface, giving them stronger shine. It's like the difference between a regular mirror and a really good mirror. Let's look at our 3 main types. Adamantine luster. This is diamond luster, and it's the superstar. The name literally means diamond-like, because, well, that's what it looks like. It's that intense, bright, almost metallic shine. Diamond reflects about 17% of light right off the surface. That's a lot. It's why diamonds look so brilliant even before light gets inside. When you see a diamond and think, wow, that's shiny, that's adamantine luster doing its thing. Vitreous luster. This means glass-like, and it's what about 80% of gemstones have. Rubies, sapphires, emeralds, they all have this type. It's a nice, pleasant shine, like looking at broken glass, in a good way. It reflects about 5 to 10% of surface light, not as intense as diamond, but still attractive. Think of it as the reliable, good-looking friend who doesn't need to show off. Resinous or waxy luster. This is softer and warmer, like amber or turquoise. The light actually penetrates a tiny bit into the surface before bouncing back, which creates that soft, organic glow. It's less mirror-like and more warm candlelight. This is common in organic gems or materials with lots of tiny crystals packed together. Two things control luster: the material's refractive index, which we can't change, it's built into the stone, and the polish quality, which we can control. Even a diamond will look dull if you scratch up its surface. So remember, good material plus excellent polish equals amazing luster. Now let's talk about transparency and clarity. These two get confused all the time, but they're actually different things. Let me explain using an analogy. Transparency is about the material itself. Can light pass through it? Imagine 3 shower doors. One is clear glass. You can see through it perfectly. One is frosted glass. Light gets through, but you can't see clearly. And one is solid wood. No light gets through at all. That's transparent, translucent, and opaque. What makes something transparent? 2 things. First, the material doesn't absorb much visible light. Second, the material has a nice, uniform crystal structure without lots of tiny defects that would scatter the light. Think of it like looking through clean air versus foggy air. Fog has tiny water droplets that scatter light everywhere, making it hard to see through. Clarity is totally different. It's about what's inside an otherwise transparent material. Think of it this way. You could have perfectly clear glass, high transparency, but if someone threw rocks at it and left cracks and chips, it would still look messy, low clarity. In gemstones, these rocks are called inclusions. They could be tiny cracks, trapped gas bubbles, or even other minerals that got stuck inside when the stone was forming. Every inclusion is like a little obstacle that light hits, and when light hits something with a different refractive index, it bounces in random directions instead of traveling smoothly. Here's a real-world example. A diamond can be chemically perfect with great transparency, meaning the diamond material itself is crystal clear. But if it has a bunch of carbon inclusions or fractures inside, those will scatter the light and reduce clarity. Professional gemologists grade clarity from flawless, no inclusions even under magnification, to included. You can see the flaws with your naked eye. Why does this matter? Because for faceted stones, stones cut with lots of flat faces, we need light to travel through the stone in very specific paths to create brilliance. Inclusions mess up those paths. It's like trying to play pinball on a table with random obstacles. The ball just won't follow the right path. Bottom line, transparency is about the material quality. Clarity is about the material purity. You need both for a truly beautiful gem. Okay, now we're getting to the really important stuff. Refractive index, or RI. This is probably the single most important number in gemology because it determines so much of what we see. Let's start simple. Light travels really, really fast, about 186,000 miles per second in air. That's fast enough to go around the Earth 7 times in 1 second. But when light hits a gemstone, something interesting happens. It slows down. And when light slows down while entering at an angle, it also bends. Why does it slow down? Here's the simple explanation. Light is made of electromagnetic waves, and these waves make the electrons in the atoms jiggle back and forth. These jiggling electrons create their own waves that interfere with the original light wave, and the net result is that light moves slower through the material. The denser and more tightly packed the atoms, the more they slow down the light. The refractive index is just a ratio that tells us how much slower light travels in the material compared to air. Diamond has an Ri of 2.42, which means light travels 2.42 times slower in diamond than in air. It's like going from a sports car on a highway, 186,000 miles per second, to driving through a school zone, about 77,000 miles per second. Huge slowdown. Now here's the cool part, and this is why Ri matters so much. When light slows down as it enters a material at an angle, the light path bends. There's actually a law for this called Snell's law. But let me give you a better analogy. Imagine you're pushing a shopping cart across smooth pavement, and you hit a patch of mud at an angle. The wheels that hit the mud first slow down, while the other wheels are still on pavement. What happens? The cart turns toward the mud. That's exactly what light does. It turns when one part of the light wave slows down before the other part. Why does this bending matter? Because in a faceted gemstone, we use this bending to control where light goes. If we bend the light enough, we can trap it inside the stone like a mirror maze. Light enters through the top, bounces around inside, and then shoots back out through the top to your eye. That's what creates brilliance. There's a special angle called the critical angle. When light inside the stone hits the back surfaces at angles steeper than this critical angle, something amazing happens. 100% of the light reflects back inside. 0 escapes. This is called total internal reflection, and it's like having perfect mirrors inside your stone. Here's the kicker. Higher Ri equals smaller critical angle equals easier to trap light. Diamond's Ri of 2.42 gives it a critical angle of only 24 degrees. That means it's super easy to make light reflect internally. You just need to cut the back facets at the right angles, and boom! The light is trapped and bounced back to you. This is why diamonds are so brilliant. Compare that to quartz with an Ri of 1.54. Its critical angle is 40 degrees. Much harder to trap light. Light that would totally reflect in diamond just passes through and escapes out the back of quartz. That's why quartz looks less brilliant and can have that window effect where you can see through the center. So remember, refractive index controls the bending controls light trapping, and light trapping creates brilliance. It's all connected. Let's see this refractive index thing in action with a head-to-head comparison. Diamond versus quartz. Same cutting style, but totally different results. Diamond with Ri equals 2.42. Picture this. Light enters through the top of the diamond. Because diamond has a high Ri, the light bends sharply as it enters. It travels down through the stone and hits those angled back facets, the pavilion. And here's the magic. Those facets are cut at about 41 degrees, and diamond's critical angle is only 24 degrees. Since the light is hitting at a steeper angle than the critical angle, what happens? Total internal reflection. Every single bit of that light bounces back up. Zero light escapes out the back. It's like the back of the diamond is made of perfect mirrors. The light bounces around a few times between the back facets and then gets channeled back up through the top, straight into your eyes. That flood of light returning to you? That's brilliance. It's what makes diamonds look so bright and lively. The stone is basically a light trap that forces every photon to come back to you. Quartz with Ri equals 1.54. Now watch what happens with lower refractive index. Light enters the top. So far, so good. It bends as it enters, but not as sharply as diamond. It travels down and hits those same back facets cut at 41 degrees. But here's the problem. Quartz's critical angle is 40 degrees. Some of the light hits at angles less than that critical angle, and when that happens, the light doesn't reflect. It just passes right through and exits the bottom of the stone. Gone. This is called light leakage. When light leaks out the back, that area looks empty and glassy, like you're looking through a window. That's literally why we call it a window. The center of the stone looks see-through and lifeless, because the light you were supposed to see just escaped. Now, this doesn't mean quartz is a bad gemstone. It just means we can't cut it the same way as diamond. Quartz cutters use shallower angles or different cutting styles to work around the lower Ri. But for a standard brilliant cut designed for diamond, quartz just can't compete. The physics is simple and unforgiving. High Ri equals trapped light equals brilliance. Low Ri equals escaped light equals windowing. You can't fake it. You can't work around it with better cutting if you use diamond angles. The numbers determine the performance. This is why diamond simulants like cubic zirconia, Ri equals 2.15, and moissanite, Ri equals 2.65, were created. They have high enough refractive indices to trap light like diamond does. The brilliance you see isn't marketing hype. It's measurable, predictable physics. Now let's talk about color, arguably the most emotional property of gemstones. Why is a ruby red? Why is an emerald green? The answer involves what we call chromophores. But don't worry, I'll make this really simple. First, a mind-blowing fact. Gemstones don't create color, they remove it. Let me explain. White light, whether from the sun or a light bulb, contains all the colors of the rainbow mixed together. When that white light enters a gemstone, the stone acts like a picky filter. It grabs certain colors and absorbs them, converting that light energy into a tiny bit of heat. The colors that don't get absorbed pass through, and those leftover colors are what you see. Think of it like this. Imagine white light is a bag of mixed candies, red, orange, yellow, green, blue, purple, all mixed together. A ruby reaches into that bag, pulls out all the green and blue candies, and eats them. What's left in the bag? The red candies. That's what you see, the leftovers. So what's doing this selective absorption? Chromophores, from Greek words meaning color bearers. In gemstones, chromophores are usually tiny amounts of metal atoms mixed into the crystal structure. We're talking trace amounts, often just 1 to 2%, or even less. The most common chromophore metals are chromium, creates red in ruby, green in emerald. Iron creates yellow, green, or blue, depending on the environment. Titanium works with iron to create blue in sapphire. Manganese creates pink. Copper creates blue-green in turquoise. Here's the cool part. The same metal can create different colors depending on the host crystal. Let me give you the classic example. Ruby. The base crystal is aluminum oxide, corundum, which is naturally colorless. But when you substitute about 1 to 2% of the aluminum atoms with chromium atoms, the crystal turns red. Why? Because chromium in that particular environment absorbs green and blue light very strongly. Remove green and blue from white light, and what's left? Red. Emerald. The base crystal is beryl, also naturally colorless. Add chromium again, same metal, but now the crystal turns green. What changed? The crystal structure around the chromium is different, which changes which colors it absorbs. Now it absorbs yellow and red-orange wavelengths. Remove those, and what's left? Green. Same ingredient, different recipe, different result. It's like how eggs can be scrambled or become a cake, depending on what else you mix them with. Here's the technical part made simple. These metal atoms have electrons that can jump between different energy levels, like jumping between floors in a building. When a light photon with just the right amount of energy comes by, an electron can absorb that photon and jump to a higher level. That photon gets absorbed, converted to heat, and that color disappears from the light passing through. Different metals have different floor plans, so they absorb different colors. And the same metal in different crystal environments has a different floor plan too. There's even another mechanism called charge transfer, where an electron jumps from one metal atom to a neighboring one. The beautiful blue of blue sapphire actually comes from electrons jumping between iron and titanium atoms. These charge transfer processes are usually very efficient, creating intense, deeply saturated colors. Bottom line, color equals chromophores equals selective absorption equals the leftovers. Every colored gemstone is showing you the colors that survived the journey through the crystal. The colors you see are the lucky ones that didn't get absorbed. Pretty cool, right? All right, time for my favorite property, fire. Those rainbow flashes that dance across a diamond when you move it. That's fire, and it's absolutely spectacular. Let me show you how it works. Remember how we talked about refractive index, how light bends when it enters a gemstone? Well, here's something I didn't tell you. Different colors of light bend by different amounts. This is called dispersion, and it's what creates fire. Here's why different colors bend differently. Light is a wave, and different colors have different wavelengths, different wave sizes. Red light has long waves. Violet light has short waves. When these waves enter a gemstone and interact with the atoms, the short waves, blue, violet, interact more strongly than the long waves, red, orange. This means blue light slows down more than red light, which means it bends more. We can measure this. Instead of one refractive index number, we actually measure the Ri for red light and the Ri for violet light separately, then calculate the difference. That difference is the dispersion value. Diamond. Red light Ri equals 2.407. Violet light Ri equals 2.451. Dispersion equals 0.044. quartz. Red light Ri equals 1.544. Violet light Ri equals 1.557. Dispersion equals 0.013. Now here's where it gets cool. When white light enters a faceted gemstone, it bends. But because red and violet bend by different amounts, they start separating, traveling in slightly different directions. As the light bounces around inside between facets, this separation gets bigger and bigger, like spreading out a deck of cards. When the light finally exits back through the top, different colors exit at different angles. Move your head or move the stone, and suddenly you're looking at the angle where red exits. Red flash. Move slightly. Now you're looking where blue exits. Blue flash. That's fire. Watching the separated colors appear and disappear as you change angles. The bigger the dispersion number, the more the colors separate and the stronger the fire. Diamond's 0.044 dispersion creates about 1 degree of separation between red and violet. That's enough for your eye to clearly see distinct color flashes. Quartz's 0.013 dispersion only creates about 1/3 of a degree of separation. That's too small for your eye to really notice distinct colors. The light mostly stays white. Here's an important point. Dispersion and refractive index are separate things. You can have high Ri plus high dispersion equals diamond, brilliant and fiery, the jackpot. High Ri plus low dispersion equals sapphire, brilliant but less colorful. Low Ri plus high dispersion equals some rare stones show fire but lack brilliance. Low Ri plus low dispersion equals quartz, neither brilliant nor fiery. Some stones actually have more dispersion than diamond. Rutile has a dispersion of 0.200, more than 6 times diamond. But rutile is usually too dark and opaque to show it off effectively. You need transparency, the right body color, and good cutting to actually see fire in action. Diamond is famous because it has the perfect combination: high enough Ri to create brilliance by trapping light, high enough dispersion to split that light into colors, plus it's colorless, so you can see the fire clearly, and hard enough to take a perfect polish. It's the complete package. Think of it this way. Brilliance is the amount of light returning to you. Fire is the color of that light. Both together create that mesmerizing sparkle we love. And that's what we mean when we say diamond has good optics. It's got both properties working together beautifully. Let's put it all together with a final comparison. Diamond versus quartz. Same elements we've discussed, but now you'll see how they work together to create the overall appearance. Round 1. Luster. The first impression. Diamond has adamantine luster, that bright, mirror-like surface shine. It reflects about 17% of light right off the surface before light even enters the stone. That's why even an uncut diamond looks bright. Quartz has vitreous luster, glassier, softer. It reflects only about 4 to 5% of surface light. Pleasant and shiny, but nowhere near as intense as diamond. Winner, diamond, by a landslide. First impression, diamond makes an entrance. Round 2, refractive index, the light trap. Diamond, Ri, equals 2.42. Critical angle equals 24 degrees. With proper cutting, pavilion facets at 41 degrees, light entering the stone hits the back facets well past the critical angle. Result? total internal reflection. 100% of light bounces back up. The light is trapped like in a hall of mirrors, creating intense brilliance. Quartz, Ri, equals 1.54. Critical angle equals 40 degrees. Using the same cutting angles, much of the light hits below the critical angle and just passes through, escaping out the bottom. Result? Light leakage, windowing, and reduced brilliance. Winner, diamond again. It's not even close. Diamond creates brilliant light return while quartz struggles with light loss. Round 3. Dispersion, the fire show. Diamond dispersion equals 0.044. This creates about 1 degree of separation between red and violet light. Result? Strong, visible rainbow flashes as you move the stone. Distinct reds, oranges, greens, blues, all dancing across the facets. Quartz dispersion equals 0.013. This creates only about 0.3 degrees of separation. Result? Minimal fire. White light stays mostly white. Maybe occasional faint colors under perfect conditions, but nothing dramatic. Winner, diamond with a knockout. Quartz barely shows any fire at all compared to diamond's colorful light show. The final verdict: diamond wins in all 3 categories. And these aren't subjective opinions. They're measurable physical properties. Surface reflectance. Diamond reflects 3.8 times more light. Critical angle. Diamond traps light 1.7 times more easily. Dispersion. Diamond creates 3.4 times more color separation. This explains why diamond commands higher value based on appearance alone, even before we talk about hardness. Diamond is the hardest natural material at 10 on Mohs scale versus quartz at 7, or rarity. Now, don't get me wrong. Quartz is a beautiful and useful gemstone. Amethyst, citrine, rose quartz, all varieties of quartz, and all lovely. But optically, they're playing a different game than diamond. It's like comparing a bicycle to a Ferrari. Both will get you there, both have their place, but one is definitely engineered for higher performance. The beauty of gemology is that these differences aren't mysterious. They're physics. The numbers tell the story, and now you can read that story yourself. All right, let's see what you've learned. I'll ask the questions, give you a moment to think, and then we'll go through the answers together. No pressure. This is just to help cement the concepts. Question 1. Which property creates those rainbow flashes, the fire, you see in a gemstone? Think about it. Got your answer? It's dispersion. Remember, dispersion means different colors of light bend by different amounts, separating white light into its rainbow components. The bigger the dispersion value, like diamond's 0.044, the more the colors separate and the stronger the fire. Low dispersion, like quartz at 0.013, means the colors barely separate, so you don't see much fire. Question 2. What creates the body color, like the red of ruby or the green of emerald? What's your answer? It's chromophores, those trace metal atoms, like chromium, iron, titanium, that absorb specific colors of light. Remember, gemstones don't add color, they subtract it. White light enters, chromophores absorb certain wavelengths, converting them to heat, and the colors that don't get absorbed pass through. Those leftover wavelengths are the color you see. Ruby looks red because chromium absorbs green and blue, leaving red behind. Question 3. Why does quartz often show a window, that see-through empty area, while diamond doesn't? Think it through. Its lower refractive index. Quartz, Ri, equals 1.54, gives it a critical angle of 40 degrees. When light inside quartz hits the back facets at angles less than 40 degrees, it doesn't reflect. It just passes through and escapes. This light leakage creates the window. Diamond Ri equals 2.42, gives it a critical angle of only 24 degrees. It's much easier for light to exceed this angle and totally reflect internally, trapping the light inside and bouncing it back to your eye. Higher Ri equals easier light trapping equals no window, just brilliance. Question 4. What luster type is described as diamond-like with that bright metallic shine? Last one. That's adamantine luster. The name literally comes from adamas, the Greek word for diamond. It's that intense, mirror-like surface reflection you get when a material has a high refractive index, above 1.9 to 2.0. Diamond reflects about 17% of light right off the surface, creating that characteristic, hard, bright shine that makes diamond unmistakable even before light enters the stone. How'd you do? If you got all 4 right, congratulations! You've successfully decoded the sparkle. You now understand that gemstone beauty isn't magic or marketing, it's physics. Luster, brilliance, color, and fire are all the result of measurable, predictable optical properties. Next time someone shows you their jewelry, you won't just say, pretty. You'll know why it's pretty, and you can explain it scientifically. That's the power of gemological knowledge. Thanks for joining me on this journey through optical physics. Keep learning, keep questioning, and remember, every sparkle tells a scientific story. Until next time.